Okay, I've now unmuted myself, I think. And so you guys will note as we go along in here that the one that I have posted, I think has some, it already has some sort of marks in it where I've kind of highlighted some things, and we'll try to kind of get ourselves worked around all of that. Okay. So we spent a lot of time talking about cardiovascular disease and diabetes. Remember now that the cardiovascular disease is the leading cause of death. Cancer is number 2. Okay. Cancer is number 2. And so I think it's really important for us to spend a little bit of time talking about, is there some chance that physical activity can have some impact on either your chances of developing certain kinds of cancer or some of the things that are going to go into after we've had treatment for certain cancers. There's going to be some other things that happen, and can we use physical activity as an intervention with all of that as well? Nia.
I have a question before we start.
Okay, fire away.
Okay, so for the lab 3, what does BIA % stand for?
So that's the bioelectrical impedance measure that we're not gonna have. So you guys are not gonna be able to get a BIA. And so I will post some additional instructions when I give you guys the things on. You're just gonna have to ignore. You're just gonna have to ignore that. You're not gonna be able to make the graph where you graph your 7-site and 3-site against the BIA because we've not been able to get that one. Okay.
Okay, also for lab 3, I feel like there's discussion, like a discussion part. Do you still want us to do like a whole like lab report with the intro and everything, or just do the discussion?
Just do the discussion portion, especially given all the stuff that's going to be due on Friday. There's no need for you guys to write a bunch of extra stuff that I'm going to feel beholden because you wrote it to try to read. And what I'm really interested in is, can you do the calculations? Can you make a couple of graphs? Can you kind of interpret what those things are pretty well? So no, don't worry about that.
Okay.
I was just going to ask, does that also apply to the final project, because it asks to calculate BIA and all that kind of stuff?
So there should be a given BIA in there, Savannah.
Okay, maybe I just didn't look close enough. Okay.
And I can look during our break, but it should be given to you.
Okay. Sounds good.
Okay. Other questions? No? Okay. All right. Let's talk about cancer a little bit. And what you guys are going to see is exercise and physical activity can have some potentially positive outcomes as it relates to cancer or very specific kinds of cancer. Unlike cardiovascular disease, though, okay, there's not going to be, because of the nature of how cancers arise most of the time, we're not going to have nearly as much of an influence. Okay. You're going to get cancer from mutations in DNA and cells beginning to divide uncontrollably. And the pathology of how that happens, right? If you're exposed to radiation or you're exposed to certain chemicals or something that cause those things to happen, there's not a lot that exercise can do to intervene. Okay. And so that's why there's not going to necessarily be these positive outcomes on all kinds of cancers. Now, the pathology of how certain types, so you guys are going to see specifically breast cancer, okay, and colorectal cancer, and to a small extent, maybe prostate cancer. There's going to be some potential because of the things that put us at risk of having those things develop. And we'll get into that just very, very briefly, okay? But it's not kind of widespread in the way that we can use exercise to essentially treat all type 2 diabetes. So we can use exercise to treat all kinds of, or prevent in some ways, all kinds of cardiovascular disease. Because of the nature of the pathology of cancer, then it's only going to work in certain very specific instances, okay? So you guys have probably all seen this before, okay? But a cancer is an abnormal, uncontrollable growth of tissues. It's a group of cells, okay, that are going to form what we oftentimes call a tumor, okay? Oftentimes called the tumor. So all of the cells, when I say that, almost all of the cells in your body have the potential to become cancerous, because almost all of the cells in your body have the potential, if given the right signals, to begin dividing and replicating themselves. Okay. Most of them don't do that often. They only do it in, certain under certain very kind of specific circumstances at very certain times. Okay. But they all have the potential for that to happen. And so that's a key thing to remember. It's why we see cancers in a whole host of cell types and tissue types and things like that. Okay. And so what happens is we're going to classify how we name cancers based upon the type of cell, right, that they're going to originate from, right? So about 80% of all cancers are going to come from what we call epithelial cells, the cells on the inside of your cheek, epithelial cells, okay? Cells that tend to be on the kind of on the surface of a lot of different tissues. And so epithelial cells are called, when you have a cancer of those, they're called carcinomas, okay? If we have hematopoietic cells that are coming from the bone marrow, so cells that produce red and white blood cells, that's leukemia. All right. Things that come specifically from white blood cells or lymphocytes is called a lymphoma. And then things that come from connective tissue, from mesenterical cells, are going to be called sarcomas. All right. And so typically you will say, like, you have a something carcinoma. So it's going to be the cell type that it originates from and the tissue of origin. And so we're gonna have those kind of named in those particular ways. So if you see names of cancers, which can be important when they're diagnosed and things, that's how they're going to get named. Okay. Some scary facts. About half of all men and about a third of all women will develop cancer at some point in their life. Guys, we can make an argument that our prostates, just from the time we're born, they're growing, that our prostates are just cancerous cells, no matter what. Whether or not they actually divide fast enough to get us to that particular place is to truly, truly be considered like what needs to be treated as cancer is going to be a little bit different. Okay. So they account for almost 25% or about a quarter of all deaths. And the good thing, though, is that even though we're accounting for all of these things, so cancer survivorship is measured in the number of years post-diagnosis that you manage to continue to live. And so typically they're done in kind of these 5-year buckets. And so the 5-year survival rate, so the number of people that will live an additional 5 years after diagnosis, okay, that number is increasing, and it's up to about 2/3 of people that have been diagnosed with cancer will live another 5 years. Okay, we can look at numbers then at 10-year survivorship, 20-year survivorship, et cetera, et cetera. And as we go on with those, the numbers do tend to decline. But we're getting better. We're getting a lot better at kind of treating and dealing with cancers. Okay, so when we talk of cancers and tumors, we usually put them into two groups. There's benign tumors, and there are what we consider to be kind of truly cancerous tumors or malignant tumors. Benign tumors, they grow really slowly. Their cells look mostly like regular cells. They're just kind of an extra kind of ball of those cells. They're kind of have these nice clean edges. When you look at cancerous cells under a microscope, that's one of the things that you're looking for is, do they have nice, well-defined kind of normal cell-like edges on them? That would denote a benign tumor. Malignant tumors grow really, really fast. And because they grow really fast, they kind of look like an amoeba or something. They're just pushing pieces of themselves out all over the place. And then malignant tumors are going to have a capacity to spread from their tissue of origin into other tissues. And so you may have lung cancer, but the cancer in your lungs actually originated in your liver or in your throat or something like all of that. And so malignant tumors are the ones that are going to be really, really dangerous. Okay. So the way that most cancers develop is there's a mutation. So there's some kind of a genetic change in the cells. So as I said, all cells have the capacity in their DNA to replicate themselves if they're given the proper signals. Most cells, they only divide and replicate themselves or repair themselves at very specific times under the influence of very specific signals. in cancerous cells, we get a change in the DNA. So you get a mutation that can be caused by a whole host of things. You get that genetic change, and it tells the cell to start replicating itself. And it can then go from one cell, right, and go from 1 to 2, and then 2 to 4, right, 4 to 8, and you get this, what we would consider in some ways exponential growth out of all of this. And then before very long, we have this massive ball, this massive kind of tumor full of cells, okay? And because the mutation is in the original one, every time it replicates its DNA, it's going to continue to include that mutation in the DNA of all the cells going forward. So they're all going to stay kind of turned on like all of that, okay? So that's how cancers develop. So I'm not really going to spend much time talking about nucleus and how cells end up dividing and those kinds of things. I'm not really going to talk about the cell cycle. The process of a cell doubling itself is called mitosis. You don't really have to know what G1 phase and S phase and G2 phase and how we double our chromosomes and those things. You guys ideally covered all of that in Intro to Zoo or something, but it's not particularly useful for our kind of talking point purposes. Okay, so as I said, the big thing with cancer cells is that they divide when they shouldn't. Okay, all of your cells have a host of safety mechanisms in them. Okay. If you want them to grow, you want them to replicate, you have to do one of two things. You've got to turn on the process of making it replicate. Okay. So there's going to be some genes in a cell that code and say, hey, start proliferating. There's also going to be, so you need to either flip the on switch on, basically, or there are going to be some genes that are what we would call tumor suppressor genes, and their job is to detect and stop cells from replicating. So if you get a mutation in the tumor suppressor genes, then the stop signal, the cell never sees the stop sign. It never sees the red light or the stop signal. And so it never gets shut off. The lights are on and we've broken the switch. And now you can't turn them back off. So either one of those things can lead to whatever that is. And so the source of those genes getting either turned on or where the off switch doesn't work is going to come from a mutation. And those mutations can come from a host of different places. All right. And there's going to be cellular metabolism. So the generation of oxygen free radicals and things can do this. And then exposure to different kinds of radiation. So ultraviolet light, ionizing radiation, so something like X-rays or nuclear, like a nuclear bomb or something. Okay, that's going to be ionizing radiation. Exposure to a host of chemicals. Okay, lots of industrial chemicals that are used, things that have like benzene rings in them and stuff. Lots of things in that area can cause DNA mutations, and then some of them are just natural errors. Every time a cell replicates its DNA, there's a reasonable chance that when you're doing millions upon millions of base pairs that you might make an error. Okay, so most of these things, every one of us probably has cancerous cells or cells that are dividing when they're not supposed to be in our body right now. And most of the time, we're going to catch those things and either repair the DNA, or we're going to catch them and we're going to tell those cells to just die. Okay, so this happens much more often than we think. But that's kind of how these things are going to come about. Okay, so this is going to talk about those kinds of things. So the genes that tend to get turned on, that are going to lead to uncontrolled cell growth, are oftentimes called oncogenes. Okay, oncogenes. These are things that they control cell growth. So you turn it on and your cell is going to grow uncontrollably, even if you don't want it to. And we talked about tumor suppressors already. Talked about those things. Okay, so let me see if I can. Okay, no, I can't erase those things. So let's talk about what puts a person at risk for developing cancer. One of the big things is heredity. Cancers tend, especially things like breast cancer and prostate cancer and things like that, tend to run in families. but it's a relatively small percentage. Um, but you typically do not pass mutations on from parent to child. Okay. The biggest cause of cancer is exposure to environmental, what we would call carcinogens, or things that cause mutations. Okay. Some of the most common carcinogens are tobacco, ultraviolet light, and then pollutants and chemicals. But then we have other things like diet and being sedentary, alcohol consumption, and then hormones. And there seems to be some interaction, especially between estrogens and testosterones and obesity, and their kind of role in cancers that are going to be related to cells that are under the influence of estrogen and testosterone. So cells that are under the influence of sex hormones. So think, right, think prostate, testes, okay, or testicular cancer, prostate cancer, breast cancer, ovarian cancer, endometrial cancer, uterine cancer, things where there are tissues that are under the influence of those sex hormones. And part of that is due to the fact that those hormones tend to drive a lot of cell division. And so we can, from some of that, make some, kind of make some assumptions on things. Okay. So if we look at this is, I think, a thing that's in the study guide. The most deadly kind of cancer, kind of rate statistics per 100,000 people is lung cancer, because there's just not a good treatment for it. And then the two next most deadly kinds of cancer are breast cancer and prostate cancer. And a lot of that is not that they are terribly, terribly nasty, although they certainly can be. It's just that so many people get them. You will see in the next couple of slides that breast cancer and prostate cancer are by far the most common forms of cancer. Okay. Then we have colorectal cancer, again, because it's pretty common. Then pancreatic cancer. Really, lung cancer and pancreatic cancer are the ones that they're not as common. Lung cancer more so because of smoking and things. Pancreatic cancer is not that common, but it's really, really deadly. Um, and so if you were to express these not per 100,000 people, but as a percentage of people that actually have those kinds of cancers, pancreatic cancer would be number one. It's the most deadly for the people that actually have it. And then you can see some of the other ones that are going to be there. Here's cancer incidence. As I said, kind of the two most common, right? Way out here: breast cancer, prostate cancer. These are going to be the things that we tend to encounter. A bunch of lung cancer because of smoking, for so much. And we'll talk a little bit about colorectal cancer in a few minutes, which is one of the ones that we think may have some influence from being sedentary and being obese. Okay. So we know that, as I said, that exercise can moderate and reduce the risk of certain ones. Part of what it can do is it can play a role in your hormone levels. It can moderate insulin levels in the same way that it does for treating type 2 diabetes. It can be in some ways helpful for moderating estrogen, and then if done excessively, it can help moderate testosterone levels. We'll talk about that a little bit, with prostate cancer, but you have to be really, really, really active before you're going to begin suppressing testosterone. Probably the biggest things that it can do is help with insulin. It can decrease weight and adiposity. We know that excess body fat plays a big role, especially in premenopausal breast cancer. Kind of the interaction between estrogen and adiposity can really be influenced by exercise. Um, from a colorectal cancer standpoint, the thing that exercise does is it decreases intestinal transit time. And so what this means is, and this is a difficult one to keep straight, is that when you exercise, food moves through your intestines faster. Okay. So the more you exercise, and this is going to seem a little crass, but the more you exercise, the more you poop. Okay. Or the sooner after having had a meal, you have to poop. And so by doing that, the food spends less time in your intestines. Okay. And by spending less time in your intestines, there is a reduced amount of time for which any kind of chemicals or carcinogens that might be in the food can get absorbed into your body and into those particular cells. So that is one of the ways we see like some of the largest influence of exercise is on the decrease in colorectal cancer risk. And that's going to be one of the big things that's there. And then also exercise can improve immune function. One of the jobs of your immune system is to catch these cells, these cancerous cells, before they really become dangerous. And so we use natural killer cells and some other kind of white blood cells to help us catch these things that are replicating when they're not supposed to be. And so up to kind of really, really excessive exercise does have some improvements in immune function. Okay. So as I told you, one of the big things that we are now beginning to understand is this role of obesity. Okay. And that's where we think that exercise can have a really positive effect. There's definitely some links to premenopausal breast cancer, endometrial cancer. So these two things are going to be, there's this interaction between adiposity and estrogen, which we'll talk about in a minute. And then colorectal cancer. So when you're obese, you've eaten more food, there's more stuff going through your small intestine and your large intestine. And so there's more exposure potentially to carcinogens and things that are going to be in food. Your next question may be, well, Dr. Black, what are the things that are in food that are going to be carcinogens? And can we avoid those foods? And my answer is I'm sure I'm sure that there are, but I'm not 100% familiar. I'm not sure that we have a lot of consensus. It's not exactly like what it shows. See here in our pictures, where basically they're like French fries or the equivalent of cigarettes. I don't know if there's anything necessarily about French fries, but there may be something to saturated fats and things that are going to lead to greater obesity. And obviously, if you're eating foods that actually have been sprayed with some sort of environmental carcinogen or chemical, that can be a real problem. But I don't necessarily know that having organic food or things like that are better or worse necessarily. It may all be kind of what are the things that are put in there in that way. All right, so we've done those. So what they're gonna talk about, right? This is obesity-related cancers. And so all obesity-related cancers are here. No, I'm sorry, I did this incorrectly. So it's postmenopausal breast cancer that's associated with obesity. My apologies. So there's something about the being obese and having a lack of estrogen. But all obesity-related cancers, right? We're at about 170 per 100,000 people if you look at some of these kinds of things. Okay, and so that's a big deal. Obesity, much like smoking, are kind of the two kind of big causes that are gonna get in there. We talked about these things. We talked about colorectal cancer. Here is breast cancer. So with colorectal cancer, exercise has maybe somewhere between a 30 to 50% reduction in the incidence of colorectal cancer, which this is typically the largest reduction that we see. So exercise is most effective at preventing colorectal cancer. Breast cancer, there's these data are a little bit old, but I don't know that we have found a whole lot. There's about a 20% reduction in risk, especially in postmenopausal women, where it's going to be driven a lot of these things. So if I want to decide, and ladies, this is going to be maybe a little spooky for you guys, and so no one has to answer, but here's what I want all of you guys to think about. Okay, we could line all the ladies up in class, and I could make a pretty reasonable assessment of who is at the most risk of developing breast cancer, not by asking if you have a family history of breast cancer, not by getting your weight or your BMI or anything else, but simply by asking, how old were you when you first had your period? Okay. And so if we line you guys up by women, the younger a woman is when she goes through puberty and has her first period, then the greater her risk of developing breast cancer. Okay. I know that seems kind of crazy, but there's where we are. And there's something about the more times that you have those cycles of rising estrogen and progesterone and ovulation, and then sort of non-fertilization, and then sloughing of the lining of the endometrium and things, that cyclic things, the more number of those cycles that you have in your life, then where you're going to actually ovulate, then the greater your risk of developing breast cancer. So I am just down the road from them here in Arkansas. Anybody aware? Anybody ever see the TV show about the Duggars who live in Springdale, Arkansas, right? And they have like 40 kids. I don't think they have 40, but it's like 21 or 22. Mrs. Duggar, I've forgotten her name. She was basically spent her entire adult life pregnant. Okay, her entire adult life pregnant. Guess what you don't do when you're pregnant? You don't ovulate. Okay. And so she is at a very, very, very reduced risk by being pregnant so much of developing breast cancer. Okay. And so that's a thing we need to kind of think about in the midst of all of these kinds of things, is we can predict it based upon that. And one of the things that exercise can do is there's evidence that adolescent girls that are more active as they enter into puberty tend to mature a little bit slower, which is an interesting fact. But girls that are more active when they are 10, 11, right, kind of that age, may tend to be a little bit older when they have their first period. And so so there's just some of the ways that physical activity can kind of help us out in some ways in the midst of all of this. Okay. Okay, prostate cancer, a little bit of a reduction, but you've got to be really, 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 really active in order to actually decrease your testosterone levels, and then that may be helpful. So if you're not a marathon runner, it's probably not doing a lot. There's some interesting data on lung cancer, but it's confounded by smoking. We have a hard time controlling for people that smoke. Lung cancer, physical activity seems to be good at reducing your risk of lung cancer in people that have not smoked. So there is a group of people that can get lung cancer that have never smoked, but smoking is the single largest risk factor for it. Even in people that have been smoking or have been smokers, there does seem to be potentially some reduction in risk in the midst of all of this, simply by, strangely enough, exercising at high intensities seems to block some of the pathways, this AKT-mTOR pathway, which drives cell proliferation. AKT and mTOR, this is the primary thing that makes your muscles get bigger. And so under normal resistance training circumstances, exercise in that way activates AKT and mTOR, but it seems like in lung tissue and those things, that kind of high intensity exercise may blunt some of that, which may prevent some tumors from going. So there's some interesting stuff that's there. If you guys are really kind of fascinated by all of this, there's a lot of really interesting research going on at the Health Science Center in Oklahoma City, at the Stevenson Cancer Center. We have a meeting with a group of them. I think it's next week we have to go, but we're doing a thing with physical activity, obesity, and several different kinds of cancer. They want to collaborate with some of us in our department. And we've done a little bit of stuff with them in the past with some breast cancer folks, but this is mostly going to be, I think, focusing on pancreatic cancer, and some things like that. So there's some interesting opportunities for doing internships or kind of mentored research experiences up there if you guys want. Okay, so that's cancer. Anybody have any questions about that? I know I ran through that really quickly, but that was in some ways kind of the point. Anybody have questions about physical activity and cancer? You can watch the other video where we go much slower and go into a lot more depth in things. Nobody cares. Okay. So the other one that I put up that was supposedly for yesterday is about physical activity and aging. And so I usually like to ask people at this point, what do we think it means to age? Right? I'm older than you guys. What does that mean? What do you think that means?
That our bodies mature.
Your body's mature. Okay, that's reasonable, Gavin. But why am I older than you? How do we define that?
Does it have to do with like your cells not dividing as much, or like collagen?
It could at some point, Julia. It could, sure. Anybody else? What does it mean to be older than someone?
I mean, you were born before I was born.
I was born before you were born, Savannah, right? I've been alive longer than you. I've accumulated more time here than you have, okay? And so in that particular way, that part of aging is in some ways inevitable, right? Like you were conceived and then born and you've been here and you're going to be here until you die. And that part, we're all screaming towards aging and death at an alarming kind of rate, right? The clock is just, the sands of the hourglass are just going on us here. Okay. But there
I
are
would
some other
also
things.
say lifestyle too.
I'm sorry, Savannah.
I would say lifestyle as well.
Okay. Lifestyle. Yeah, sure. There are some other things that happen though that can go on with this is hooray for existential dread. That's right. Although maybe it shouldn't be existential dread, right? I mean, maybe it should just be this is the inevitability of what's going to happen, and so we just need to accept it and then move on.
Right, that's the alternate way of phrasing it. But the first time you were like, well, we're just like hurtling toward death. And so
right?
that's
I mean, we are. We're hurtling towards death at an alarming rate, right? Like every day. But the other thing that we need to understand that occurs with aging is that kind of like what Julia was getting at and a little bit of like what Savannah said, and I apologize, I looked at the chat really quickly, but whoever just put something in the chat is that there may be changes in tissues and changes at the cellular level and at the organ level that are also going to be a part of this kind of natural process of I have been here longer. Okay. Much like this stupid thing here in my beard is betraying me in many ways on all of this. Up until a few years ago, basically until my daughter got here, I didn't really have any gray hair in my beard, and I could maybe pass for somebody that was like 25 or 28. I could pass for a grad student still. It is not happening any longer on those things. Okay, and so what this lecture gets at to a reasonable extent is kind of what are those expected changes? What are the things we have some level of control over? Because there's some very specific things like changes in muscle mass, changes in strength, okay, that are going to tend to occur as we get older, but are not inevitable. They don't have to be inevitable. And that's the kind of the big take home that I want you guys to get from this is, look, you're going to get older. In general, we lose muscle, we gain fat, we lose strength, we lose agility and speed and balance and those kinds of things, right? And at some point, we tend to lose enough of those that like I can't stand up out of my seat without like the help of a walker. I can't walk, much less run. I can't get onto and off of the toilet. I can't take a shower. I can't get into and out of the bathtub by myself, right? That there is some basal level of strength and function that we need. And at some point, as part of the aging process, we may actually lose some of those things. There's some inevitable aging that takes place from a metabolic standpoint. There's some inevitable aging that takes place, right, with our drop in maximal heart rate. So our VO2 max has to decline as we age, assuming your state of training is going to be the same. So those are kinds of the big take homes. Okay. You lose muscle. This is called sarcopenia, right? It's called sarcopenia, the age-related loss of muscle mass, right? So, ladies and gentlemen, however much muscle you have right now, you've probably peaked, okay? Guys, there's a very reasonable chance that you guys are already declining in your testosterone levels. And a lot of the age-related decline in muscle mass is due to falling levels of testosterone, and then ladies post-menopause, falling levels of estrogen. So the decline in testosterone with aging is called andropause. It's very similar, occurs at about the same time frames as menopause does. Although to be honest, guys, testosterone usually peaks between like 16 and 18. So you guys are all already, for the most part, past your prime. Let that sink in for a minute, okay? And you're also going to tend to lose activity as we age. So sarcopenia tends to be due to the combination of reduced activity, reduced resistance training, and reductions in testosterone and estrogen levels. So this is kind of the double whammy of those things. We have all sorts of positive evidence that if you maintain activity and you continue to resistance train, you can either maintain or potentially in some people increase muscle mass up into maybe your 70s or your 80s. Some of the data on people in their 80s is they can keep the muscle that they have, but they may actually lose the hypertrophic effects when they get into their late 70s or their 80s. There's a group that's at Ball State University in Muncie, Indiana. They do a bunch of stuff on aging. Weirdly, they also are the guys that get to go do a bunch of stuff with all the astronauts that have been on the International Space Station and things. But they have evidence. They have guys and women come to the lab at like 80, and they have them doing squats and leg press and knee extensions and things. And then they take muscle biopsies from them. They do a lot of fun stuff. And they found that kind of up through maybe your mid 70s, you can potentially continue to increase muscle mass, especially if you've not ever done a lot of resistance training throughout your life. Okay. But from a sarcopenia standpoint, right? If you can, the decline in testosterone, at least legally at this point, is pretty difficult for us it's going to happen, right? Ladies, menopause is coming for you, right? You can be my mom and you can take the hormone replacement therapy for a while if you want, but there's not a lot. There's some potential drawbacks from like a development of cancer and cardiovascular disease standpoint of taking testosterone replacements and estrogen replacements. I imagine at some point, probably by the time y'all are old enough for it to matter, that we'll have gotten better at kind of figuring out what the proper kind of low dose of those things may be to kind of maintain stuff. But we can prevent a lot of that age-related decline, okay, if you stay active, if you resistance train. And especially for women post-menopause, as we will see probably tomorrow when we do skeletal stuff, not only can we prevent the loss of muscle mass, we can prevent some of the loss of bone mineral density and the development of osteoporosis, okay? So it's really, really important that we kind of get at some of those things, all right? Okay, let me just kind of move through this. So what I want to try to point out to you guys, okay, and make an appeal in some ways to you about is, if you look at these graphs, okay, one of the things that also tends to occur, and it's partially related to disuse and it's partially related to the loss of muscle mass as we age, is in the left panel here, we have sort of maximal knee extensor strength, right? So this is, if we had you do squats, most people are going to tend to be their strongest, okay, in their early 20s, say 18 to 25, kind of where you guys are right now. You're probably about as strong as you're ever going to be. In a very general sense, for people that have never done resistance training, you pick up resistance training next week, you're absolutely going to get stronger. But if we look at as a person ages down here, okay, on the x-axis, what tends to happen is there's a relatively, they've drawn it as being linear. It's really not linear. It's more of a thing that looks like this one on the right side here, where what it really should probably be is a thing where it's kind of gradual, and then it falls more like this, okay? Where it's not kind of this sort of straight precipitous decline, but you lose strength as you get older, okay? And the really important thing to keep in mind is sort of what this box, this red box here in the middle is. So in order to do certain activities, okay, whatever they might be, you need a certain amount of strength and you need a certain amount of sort of additional strength to perform that activity quickly. Okay, so they're going to talk about doing an activity fast versus doing an activity slow. So going from sitting to standing up. Okay, so if I told you guys to stand up, but stand up slowly, that requires, in some ways, less overall strength than it does to stand up really, really fast. Because remember, when we want to go fast, we actually generate less force. So you got to have a larger maximal to be able to do that. Okay. We know that going from sitting to standing at a certain speed is predictive of risk of falling and hurting yourself, quality of life, a whole host of different things. Okay. And so what we know is that there is this zone where when your strength falls to some specific amount, you're no longer going to, like right in here, you're no longer going to be able to stand up as fast as you'd hoped or as fast as you used to be able to. Okay. So there's some threshold amount of force that we need to do it, and then some threshold amount of force that we need to do it quickly. And then at some other point, we're going to get down here, and there's some threshold amount, right, that if you fall below that, then you can't even stand up out of a chair. All right. And so that's the stuff that we are trying to avoid, okay, with aging. That's the place that we're trying to avoid by using exercise to kind of counteract some of this natural age-related decline in both mass and strength. And there are two ways to go about this, okay? There's two ways. The first is what is, I'm going to show you guys in the one over here. And what you guys see in the blue line right here is people that are strength trained from an early age. So you guys are going to go into resistance training now, then you're going to stop, okay? And if we compare you to people that have never resistance trained, who never take it up, you see this kind of relatively similar slope of decline over time. But because these people start at a higher level with this natural decline, they're still going to be a lot stronger out here at 80 than are people that began at a much lower level. So if you can build up some mass and build up some strength now, you've got more to lose as you age, okay? The other way to get around to this is I've got my untrained person or my strength trained person, and what I'm going to do is we've got another group of people, and we'll put them in here, and I'm just going to kind of keep resistance training over time. And I'm going to try to hold on to whatever it is that I've got. And then there may be a little bit of a decline that's kind of a natural progression. But if I can either take it up or I can continue to do it, then I can hold on to whatever I've got, even if I'm not a power lifter, even if I'm not somebody that has giant muscles and all of this maximal strength, I can hold on to whatever I've got right now for a much longer kind of period of time. And I can sort of level off that slope of decline that we may see with age. Okay. All right. Does that make sense to everybody? Does that part of it make sense? The kind of two ways to approach those things. Okay.
Yes.
At least it makes sense to Nia. That's all that I really care about. One person. I got through to one person. Okay. We talked about sarcopenia. We've kind of gone through these things. So a weird thing happens. We've talked about this already once, but a weird thing happens with older people. So as a part of losing muscle mass, okay, you tend to preferentially lose type 2 muscle fibers. So you tend to lose fast twitch muscle, okay? And you tend to see, in addition, a shift from 2X in whatever you have to more 2A fibers. But if we look at people, most people are going to see this kind of progressive increase in type 1 muscle fibers with age. So your type 2s go down and type 1 tend to increase, okay? So part of this is driven by the fact that as you age, we all accumulate neurotoxins, okay? From food, from the environment, from exposure to a bunch of different things. And so we accumulate this neurotoxin. Excuse me. And as you accumulate those, your motor neurons in your spinal cord will die. And for whatever reason, it seems like that motor neurons that connect to type 2 fibers are more susceptible to neurotoxins and death than those that go to type 1s. And so you've got one, right? So I've got trying to draw this here, but I've got a motor neuron, right? It's going to send its axon out and it's going to connect to a couple of these muscle fibers. Okay. If this one dies, what tends to happen is, and so this is a type 2, is I have an adjacent motor neuron and it's type 1, and it was going off out here to some different muscle fibers, is that when this one dies, then this connection here is going to be lost. And so what happens is these type 1 fibers will branch off axons and try to reconnect those fibers. And so you get type 2 fibers that get connected to a type 1 motor neuron, and that drives a change in their fiber type from type 2 back to type 1. It's a really fascinating kind of thing. And so there's some interesting consequences of that, but the big issue is just that older people tend to have more type 1 fibers. So what does that mean I'm not very good at doing when I get old? What would that fiber type shift make it more difficult for me to do? Chandler, what do you think? If I have more type 1 fibers than type 2 as I'm aging, what am I not going to be as good at?
Force production.
Okay, I'm gonna lose force. Good, that's 1. Jacob, what about you? Can you think of something else?
I don't really remember.
You don't remember. Okay. Anybody else? Anybody remember? If I have more type 2 fibers, what am I better? Like, what am I a better athlete? What events are going to be better for me than if I've got a bunch of type 1s?
Events that require like fast contractions.
Okay, fast contractions. Okay. Any of you guys maybe see your grandparents over the weekend? Are they slow? They move around slow? You ever have to drive in the car with them and their reaction time is not as good, right? Some of it is purely physical. It's not a mental thing. Like they've lost some of their type 2 fibers, so they can't run, they can't jump as fast or as high. Their reaction times have gone down. And so these are some of this kind of the natural consequences that will accompany these things. Okay. Aging in the skeletal system, we're going to talk a lot about that tomorrow. The other thing that happens is you're going to get some neuron death, both in the brain and the spinal cord. And so because of all of that, essentially everything that is controlled in the neuromuscular system by your brain, everything slows down, everything becomes worse. So you have fewer neurons, your reaction time goes down, your coordination goes down, your dexterity goes down, and all of that's going to make it more difficult for us to walk, to run, to drive, okay, to do fine motor skills and those types of things. The good thing about all of this, though, is if you keep doing those things, if you keep doing the things that require a lot of nervous system signals, you can prevent a lot of that loss. Okay. So here's Gramps with his awesome mustache. He's about to do some deadlifts. Going to get after a little bit. And as we've said, 100 times, basically, strength training in the elderly is really, really good. It doesn't take that much to see these kind of really, 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 really profound improvements. To that end, here's one of the original studies on really, really older people in exercise. It was published in JAMA, which is the Journal of the American Medical Association, in 1990. But they took people that were between like 85 and 95 years old. They're these old, frail people. They lived in a nursing home. Okay. They all had osteoarthritis, osteoporosis, coronary artery disease, hypertension, all of these secondary chronic diseases. They did 8 weeks of training in them. Okay. And they did them only doing knee extension, but they worked at about 80% of their 1 rep max. And they found these really, really profound effects. Their knee extensor strength went up, somewhere between 150 and 200%. Okay. Their walking speed went up. A couple of them after 8 weeks no longer needed aids for walking. 3 of them were able to get up out of a chair when they couldn't beforehand, right? We were having these really profound effects in these very, very, very old individuals simply from doing this kind of resistance training. And in older adults, lower body strength is really, really important. And then enough upper body strength to be able to kind of grab things, hold on to things, and move things around kind of in your arms and stuff is really, really important. Okay. Older adults, even more so than younger adults, can really benefit, really, really benefit from resistance training. Okay. So you don't have to do high intensity stuff either. So that was at 80% of 1 rep max. That's having very old individuals do what a typical resistance training program for younger folks would be. Okay. So here's one. Okay. We have some data that sedentary elderly folks using 40 to 50% of 1 rep max. I always laugh at this study. They use 60 to 70%. Like, oh, this is lighter weight at 60 to 70%. It's not really that light. You know, you're still kind of on the bottom end of what we would recommend for regular people, but 40, 50% doing anything, okay? Doing anything in these older adults is really, really, really beneficial, okay? Really beneficial. My parents, they go to their PT clinic and work out at the PT clinic. They go and do sort of, it's not even directed there. It's not billed to insurance or anything. They just pay for like, you know, a monthly fee to go and use the PT clinic. And there are people there in case something happens, but they get a little bit of a program, but they go and do sort of rehabilitative and strength training exercises, doing all of that. And then they go to the local, my dad calls it the old folks home here, but it's the sort of fitness center that's run by the city of Rogers, and they go and they do that. My mom does water aerobics and some things. And so all of those things can be really, really beneficial for kind of maintaining strength and function. Okay. So we talk about VO2 max. Apologies. Let me just check on this one thing in chat. Okay. So we lose about 5 mLs per kg per minute in VO2 max per decade. And a lot of that is just due to inactivity and the loss of max heart rate. Those of you have your estimate, okay? You have your estimate. Some of you were in like the mid 30s or thereabouts in your VO2 max. The functional threshold, so the VO2 max that you need, that you need to be able to just like get up and walk around and do the most minimal of things is maybe 12 to 15 mLs per kg per minute, okay? That was what we would call a functional threshold. So those of you guys that are in like the mid 30s, okay, you've got, if you lose 5 per decade, then if you follow this normal pattern, then where you're going to be is if you lose 5 per decade by the time you're about 60 or thereabouts, you're going to be in a place where you are very, very near your functional threshold. So you need to be able to maintain activities and do some things to prevent some of this loss in VO2 max, which we can very much do, okay? Some of this is due to heart rate. A lot of it is due to drop in max heart rate. A little bit of it is due to atherosclerosis and some changes in arterial function. You may have weakened respiratory muscles. Your diaphragm may become weakened. There may be some stiffness in the costal joint, so you lose some elasticity and stuff in your lungs. But a lot of this can be prevented if you'll just stay active. If you'll just do some very minimal things like walking, even you can prevent a bunch of these kinds of things. Okay, this is Dr. Pinku's father, who's a member of the Israeli Walking Association. On all of those kinds of things. And so they do a whole bunch, but we know that if we kind of maintain all of this, that we can, it's this idea of if you use it or lose it, that if you stay active, then you can maintain a lot of your functional capacity. I was looking for it this morning and I couldn't find it. I had a video, I found a picture, but I couldn't find the video. They showed us at one of our national meetings. There's a guy who's a famous exercise physiologist. He was 95 years old and they had him on a bike and he was doing a VO2 max test on the bike at 95 years old. They had him hooked up to an EKG and all of these things. And at 95, his VO2 max was like in the mid 30s, which is just unfreaking believable that it was going to be that high. And so you can maintain this if you stay if you stay active. My dad is 74 now. And he goes and has a stress test done, a cardiac stress test done every year. And for the most part, he rides his bike and swims and does enough stuff that he basically maxes out the stress test. Like, he's off the chart on those kinds of things. And I mean, he's going to live longer than I am. He's a crazy superhuman in some ways, but it's just kind of a testament to that if you stay active, we can prevent a lot of these kinds of things. Okay, so the last couple of things in here that I want you guys to be aware of is there are a lot of different ways, and people have spent a lot of time doing this, trying to come up with tests, okay, to figure out how well is a person doing as they age. We've already talked about this functional VO2 threshold and these functional strength thresholds to perform certain what we call ADLs. An ADL is called an activity, okay, of daily living. This is just stuff you do in your everyday life that we mostly take for granted. And so one of the best ways to test all of this was developed by a woman who was on my dissertation committee. I'm at the University of Georgia. And so we would go around and go up to her lab and play around with this. It was pretty interesting. But they developed something called the CSPFP, and that stands for the Continuous Scale Functional Performance Test. And there's been a bunch of derivations of all of this. And she developed this as part of her dissertation when she was at the University of Washington. But what they did was they measured people's strength, they measured people's VO2 max, and then they asked them to do a bunch of different tasks, and they tried to score people on how they did those tasks, and then use some statistical sort of equations to model what is the minimum amount of strength and the minimum amount of VO2 max to be able to perform these activities pretty well. And so this is just the graph showing you how you will note that they look at people with their peak oxygen consumption, and their PFP score is here and their VO2 is down here, right? And you will note that people that had very low PFP scores are going to be in this area. People that had very high PFP scores are up here. And there reaches some sort of, if you fit a curve to this, you reach some sort of inflection point right about here at about 20 mLs per kg per minute. And then once you get over that, as we look out this direction, it doesn't really matter if your VO2 max is you're a really fit older person and you're like at 40, or if you're barely over 20, there's not a lot of relationship there between your PFP score and your peak O2 consumption. Okay. Here's the similar graph for how strong are your knee extensors in Newton meters or per kilogram minutes. But it's the same kind of thing, right? That there's some sort of threshold value right about here. And then after that, it's not going to be the same. So it's about 2.5 Newton meters per kilogram of body weight that we need to be able to do these kinds of things. And so this test involves, the PFP test, it involves, I think I have a picture of it somewhere. Do I not? It involves a lot of really interesting things. And we used to have a lab in the classroom in columns. They used to do all of this, but for the PFP, like you have to climb up some stairs, and we like time how quickly you can get up a few stairs and turn around and come back down. You do the 6-minute walk test. You're going to do some task where there's a fake kitchen, and I don't know what happened. Sorry. Where there's a fake kitchen, and you have to load up your grocery bag, and then you have to carry groceries a certain distance, and they figure out like how heavy was your grocery bag and how far did you go and how long did it take you to go. And so it mimics that. There's a part where you have to make a bed. There's a part where you have to get clothes out of a dryer and fold them. You have to bend over and pick stuff up off the floor. You have to get into and out of a chair. I think what the other ones are, but they're these things that you do every day in your life, and you get scored for how much of it can you do and how quickly can you do it. And it's basically impossible to get a perfect score. Like, we would know how the test would go. We would go up there and try to get a score that would be 100 on it, and you really can't. It's almost impossible. But it's very, very functional in this particular way. Okay. And so you can make these up. They made modified versions of this for people that had a spinal cord injury, for people that, need a walker. There's modified versions of these for kind of pretty much anything. Would be a very easy thing to put in like a PT clinic or an OT clinic or a hospital, and assess people, and then work on particular training and activities that are limiting people from doing all of this. Okay. So some really fascinating kind of stuff that goes into this, and trying to do these very functional kinds of movements. Okay. And there's multiple versions of this. People have developed other ones. There's questionnaires and stuff that we ask people that we try to come up with. Like, it's going to ask you, can you do this? Can you do that? How long does it take you to do this? Do you have a walker? Do you need help? But the big take home is just that as we age, your ability to do all of these things is typically going to decline. But if you maintain exercise, you can kind of prevent a lot of that. Okay. Okay. So that's kind of all. I just wanted to really hit the high points of those things for you guys. And so what we're going to do is, let's take a break until noon, and then we'll do a little bit of, let's do this. Okay. Let's do this.
Dr. Bob,
So yes.
sorry, can you publish the lecture for this one on Canvas?
Of course. Did I not do that? That seems like something that I would not do, doesn't it? That sort of reeks of me not doing that. Okay. I'm releasing all of them except for Gate to you guys. So there we go. All right. So let's do a little in class. I'm going to put you guys in breakout rooms for like 5 minutes. Okay. And in your breakout rooms, I want you to do this for me. Okay. I want you to do this. I want you to, 1, define what research is. What does it mean when something is research? Okay. And then 2, much like what we did with our tolerance for risk for exercise, I want you guys to tell me how much research showing something to be true in that way based upon research, or to be the case. How much research do you need before it's enough to change your mind and actually have you change your behavior? Okay. This is especially pertinent in some ways with sort of COVID and the vaccines and a whole host of other things. Okay. Like, if I told you guys that there was a study that came out today that said that going outside when the sun is shining kills you, would it change your behavior or something like that? Okay. How many studies, how much, what do you need to know before it's going to actually change your behavior? Okay. So I'm going to make the rooms and stick you guys in there. So I'm pausing. Okay. So tell me, I will just pick somebody. Who have I not picked on today? Sunny.
Yes.
Who's in your group?
Oh, I'm really bad. It was like John. Oh, I do not remember.
John and
everyone's
Jessica are
name.
waving. Okay.
Okay, yeah.
What did you guys, and Jenna, okay, what did you guys come up with as a definition for research?
For like a definition of research, we said like a scientific method to kind of like study maybe what you're like hypothesizing. I think that's
Okay.
what we said.
Okay. A scientific method, studying something that we're hypothesizing. How do we do research? Like, how do I study something?
Well, you can do like field research or like stuff with like like surveys maybe.
Okay. Okay. So I'll ask someone else in your group. So Jenna, if I told you, Jenna, that we need to know how often people actually run the stop sign at the closest like stop sign to your wherever you're living, wherever your apartment or your house is. How would you go about getting me that data? What would you need to do?
I mean, I would have to do an experiment where I'd sit out there and like, or be hidden so it doesn't affect behavior. And over a course of multiple days and multiple seasons with like multiple people, because I kind of live in a little bit of a college area. So I'm sure when college students are in town, it's a little different. But I'm sure that, you know, over the course of time, I'd be able to record how many people went through the stop sign, how many people actually ran it. And then I would use that data to, you know, form conclusions from that.
Okay. Okay. One, she just said all y'all weren't as good of drivers or were more dangerous, more sort of adventurous drivers than us old people. My wife says that I drive like a grandma. I do. I drive very slowly or like at the speed limit. My wife likes to be at what I call ramming speed as fast as possible. So she's very, very big on turn, stomp on the gas. And then get on the brakes really quickly if you need to. I'm very just kind of slow and we're going to ease up to things. Okay. All right. We're going to come back to what Jenna just said. We'll ask somebody else. Wyatt.
Yes.
What did your group come up with as a definition of research?
So it was kind of, I mean, ours did definitely vary. It was kind of like, so we knew, obviously, when it's like a life and death situation, research is probably more, I would say, in depth than like, you know, your casual kind of thing. We just said something that obviously can be tested, multiple tests, obviously, to have like an accurate estimate, I would say. And then we said, obviously, when you're looking at research, different like journals and stuff are going to be more respected than others and probably have, you know, more useful information than, you know, what you said. Like, I don't remember what journal you said, but some random like no name journal compared to like, you know, a health journal.
Okay. Okay. So let me ask the question in a little bit different way, and this is kind of to everybody. So, has anybody driven in your car somewhere today?
Yes.
Jessica, you're nodding your head yes. Yeah. Where did you drive? Do you mind me asking? Did you have to park when you got there? Pardon? You went to Target?
Yeah.
Okay. Awesome. Love me some Target. Probably going to go this afternoon. So here's my question, guys.
Me too.
Jessica, do you have a specific route you take to go to Target?
I do. It's like 5 minutes down the street, which is like a more dangerous game, but I literally go the same way every time. There's not really another way for me to go.
Okay. But I was going to say like you've picked that particular way. Like everybody think about the last time you went to Target or Walmart or the last time when you had to come to campus and you had to park somewhere, right? Do you take a different route or would you take a different route at different times of day? If I know that I'm going to this building and I need to park in here's where I can park, right? At this time of day, but not at some other time of day. Or here's how I'm going to best get from my apartment or house onto campus or to Target or to Walmart. Like not parking at Target or Walmart, it's kind of a weird thing. You're just going to be out in the back. Okay, but my question is that research? Have you guys done research to determine that?
I know when I go to work, I take different ways home all the time just to kind of see what's around. Is that like a research thing? Like to
That is
observe?
exactly what that is, Jessica. That's exactly right. That's research, right? You're gathering data, right? And you may think, ooh, okay, well, the last time I did this on a Tuesday at 5:30, then it took this long. So I'm gonna try a different way, right? But on Wednesdays, this, I don't know, whatever, these other people are at this place. So I say all of this to tell you guys that every one of you has been doing research your entire life. Everybody does research almost every day. Now, admittedly, you probably don't think of it as research. And I like to present it in this way in the hopes of kind of demystifying what research is, okay? My daughter does research all the time. She goes and like she touches something, and if it's hot, then she's not going to touch it again. She's gathering data, right? If I do this, even though dad told me not to, am I going to get in trouble? Is he going to take my toy away from me? Am I going to get scolded and told that I'm being naughty? Like, what's going to happen? Oh, I didn't. Okay, well, I'm gonna do something else then. I'm gonna do something else. So we are always making observations. We're always gathering data. And that was my point to come back to what Jenna was doing. In order to do research, we have to make an observation. Okay. We have to, and it's not just that you have to look at something, but you have to engage in something in order to gather information and data about whatever you might consider to be a problem. Okay. How do you learn how to do anything? Watch somebody do it, you try it, you fall over it. I didn't like that. I'm gonna do it this other way. Okay. We'll try it some other place. I live someplace new. What's the best way for me to get home when I get off of work or when I get out of class? I'm going to try this route. That one sucked, right? Because it runs by, I don't know, whatever, pick some other place. So I'm going to try a different route. But if I go at a different time of day, then that's going to be less of an issue. So I need to go this other way. We do things like this all the time, okay? All the time. You learn what we would call social science stuff, like behavioral interactions with other people. I did this and I said this what I thought was funny and nobody laughed. So I guess that's not a good joke. So I'm gonna try something different. Like we're always gathering information in that way. And so when most people think of research, what they really think of is kind of what I have written on our slide, which is this systematic way of having a hypothesis, designing an experiment, making observations, right? And then trying to draw some sort of conclusion about whether or not your hypothesis was or was not supported. Okay. And that's good, right? That's a good way to do things. It's a good way to try to make decisions and to learn things. But I feel like it also makes it seem overly formal and like it's something that's done right by these people that are wearing goggles and a lab coat, like off someplace that's not, kind of us in that way. And so people are always doing research all the time. I think that's really important. So what I'm gonna do now, before we talk about sort of how many studies we need to do something, let's do just a little bit with this. Why is it not going? There we go. Okay. So, oh, I don't have it. Why do I not have it here? Oh, I don't have it written on this whole thing. Okay, so it must be, I didn't get the right thing copied over from Capstone. But when we undertake research, it is, right, it involves observations that tend to be done in a systematic manner. So there's some rhyme or reason to why we're doing it, okay? We're going to form and hopefully test hypotheses, which we'll talk about, okay? And because of all of this, though, some studies and some research are better than others, right? Some of them are more definitive or more believable than others. And I think that's one of the biggest things that I want you guys to take away from all of this is there are some things that we need to do to make a research study better than a different one. And this is one of the reasons why I feel like in some instances that the popular press does a really, really bad job of kind of lumping all things together, or they're going to say, right, like, well, this drug company did a research study, and because it is to benefit of the drug company that the drug works, they're going to make money off of it, then we can't believe any of their results. And that's a reasonable thing to be worried about. But if you look at the methods that were undertaken and how a bunch of this stuff was done, then they may do a lot of things that are going to kind of prevent there from being bias and stuff that's going to be introduced. Okay, so in all of our studies, typically we have two kinds of variables. When you're gathering data, we're going to have an independent variable and a dependent variable. Okay, A dependent variable is the thing that we are measuring, okay? This is how long does it take me to get to class when I take a particular route, okay? When I drive from my apartment, how long does it take me? Time is my dependent variable. The independent variable is the thing that we are manipulating, the thing that we're making different between our various attempts at something. Okay. So when we think of exercise, the independent variable is how much exercise or how long you're exercising or the type of exercise, or I'm giving you this particular supplement or I'm not giving you that particular supplement. It's the thing that's manipulated. So from your apartment to get to school, how long does it take? The time is the dependent. The route you take would be the independent variable. I hope that makes sense. Okay. So most experiments have both an independent and a dependent variable. And we'll talk about sometimes we need multiple independent variables and multiple dependent variables to make our studies really, really strong. Okay. So you probably have heard these terms before, but there's an idea of something called a correlation and then different kinds of experiments that can help us get at the idea of what we would call causation. Okay. So a correlation is going to be something we derive from a particular experimental design that allows us to assess a relationship, right? As one thing changes, does something else change? Okay. Typically in correlational experiments, we as researchers are not manipulating the independent variable. Okay. On your last lab, I asked everybody to make a graph where we were taking resting heart rate and making a scatter plot with resting heart rate and your predicted VO2 max based upon the 6-minute walk test. Okay. That was and then we ran and we put a line of best fit in and we could run a correlation. So what is the strength of relationship that we're seeing between those two things, right? None of you manipulated your resting heart rate. None of you manipulated your VO2 max in any way. We just gathered all of that data and decided, let's look and see, do people that differ on resting heart rate also differ in some predictable manner on their predicted VO2 max? Okay. And we found a bit of a relationship. That's the idea of what's called a true correlational study. If I wanted to try to see, is your resting heart rate the thing that is causing the differences in VO2 max, then what I would want to do is I would need to change something. Okay. I would need to give you, say, meth and make your resting heart rate go up and then have you do a VO2 max test and see, well, if I make your resting heart rate go up, is that going to have knock-on effects on what your VO2 max is or vice versa? Okay. We didn't do that, but that's the idea. So there are different kinds of experiments, each of which have their own kind of positives and negatives that are going to come into them. So some experiments only let us draw correlations. Some are going to let us draw this idea of causation. And so that's going to be one of the things we're going to spend a little bit of time talking about today. Okay. So for a lot of causative experiments, we want to do something called a prospective study. And so a prospective study is where we find a group of people and we follow them over some period of time and we determine how those factors may, if they're similar on certain factors or they're different on certain factors, how are the changes in those factors going to alter or affect some other dependent measure. Okay. So I take all of you, you've been in my class, and I send you a questionnaire and I see how you're doing next semester in the fall. And then I see how you're going to do in the spring. Okay. And we can try to say the people that made the best grade in my class, are you also going to make the best grade in the next class or the next class or the next class? That would be a prospective study. Okay. Now, what I could also do to make it a prospective study is I could take you guys and say, I'm going to take half of you and I'm going to tutor you myself next semester. And the other half, you're not going to get any help from me. Okay, but I'm going to tutor you when you take exercise phys, and we'll see then who makes better grades in exercise phys. That would be a prospective study. Again, it's you guys being followed going forward, but I'm making each group is getting a different treatment, if you will, there. Okay. Retrospective studies are very useful, but prospective studies can allow us to look for causation. Okay. Retrospective studies really can't. Okay. Retrospective studies very much tend to be correlational studies. And so they're backwards looking. All of you guys are here right now. You all are going to make a certain grade in my class. Let me ask you a series of questions about where you went to high school, where you went to junior high. Have you had any tutoring? What classes have you had coming into my class? What grades did you make in those classes, right? What's your SAT score, your ACT score? How did your parents do when they were in high school or college or something, right? I'm looking backwards and I'm trying to look for, are there things that we can glean from your past that are common among those of you that do really well in my class and that maybe are common among those of you that don't do as well in my class, okay? So in that way, looking backwards can give us a good place to start. A lot of initial health-related studies are retrospective. We're going to look for, are there shared characteristics of the people that get cardiovascular disease? Yes, it seems to be this and this and this. They're sedentary and they have high blood pressure. Okay, well now let's go and we're going to use that to form our questions and our hypotheses. Now let's go and try to manipulate blood pressure and manipulate whether or not they are sedentary and see if that has further effects on their cardiovascular disease. Okay, that's so we use our results from a retrospective study in many instances to then design a prospective study to try to look for causation. Okay. All right. In correlational studies, and I do want you guys to know this a little bit. I know some of you may have had some classes in statistics. There may be a lot of you that haven't. I continue to think that we probably should teach research methods and statistics in a class to our own students, but a different thing for a different day. So when we calculate a correlation, okay, we are going to get two things from the statistical test. And very often what we get is it's called a Pearson coefficient. Okay. And that Pearson coefficient is an R. Now, how we get R out of Pearson doesn't really matter. Okay. But when you run a correlation between one variable and another, you're going to get two pieces of information. We're going to get a direction. So the correlation is either going to be positive or negative. And all that is going to describe for us is, does the line go down like this, or does the line go up? This would be a negative correlation. This would be a positive correlation. So in a negative correlation, right, as we go from 1 to 10 here, 1 to 10 there. As we get bigger on the x-axis, we're getting smaller on the y-axis. So as one variable goes up, the other one goes down. That's a negative correlation. In this one, if it's the same thing, we've got 10 and 1 and 1 and 10. As we go up on the x-axis, we're also going up on the y-axis. So they're changing in the same direction. That means it's a positive relationship, okay? So we're going to get a range of scores that are going to range from either -1 to +1. So that's the direction of our relationship. And then the closer to 1 we are, that's going to tell us something about the magnitude or the strength of the relationship between our two variables. A perfect correlation is 1.0, which never happens in actual practice in nature. Okay, two things should never, ever, ever be perfectly correlated. But that just means that as we get a 1 unit change in one thing, we're also going to get a 1 unit change in something else. Okay, so Things that are what we would call strongly correlated are going to get values that range from 0.7 to 1, moderate is 0.3 to 0.69, and then weak correlations is 0. If there's 0, there's essentially no correlation, and 0.29. Okay, I do want you guys to know this kind of magnitude, these ranges, and I do want you to know a little bit about kind of what a correlation is. Okay, so if you want to think back to the scatter plot that you made in lab number 2, what we saw was if we put, okay, wait, no, I didn't put it over there far enough. We put predicted VO2 on the Y, and we put resting heart rate here on the X. And what we found was some things that looked kind of like this, right? And it went down. So you guys found a negative correlation between resting heart rate and VO2, predicted VO2 max. And most of you guys, when we did it, you got an R squared value of about 0.3, which if we take the square root of all of that, then we were looking at a place where I needed to run that where we're going to have an R value, right? Your R value is like 0.6 or 0.7, somewhere up there. Okay. So what you see is when we have a strong relationship, this is some things, this is going to be your average performance rating. So imagine you have a gymnast and you have your score on the balance beam. And then down here, we have the number of sessions where you practiced your balance beam routine. If we put a line of best fit up through here, you will note that there's this strong positive correlation. The more I practice, the higher my score is. And we calculate the correlation by finding the average extent to which each one of these dots, how far the dot is from your line of best fit. And so you will note how kind of much tighter these cluster to the line. Here you're going to have roughly the same relationship, but just note here how much farther away from the line all of our individual scores are. So the R value is going to be a little bit smaller. And then here in our weak correlation, you would draw it sort of like this, okay? But there's really no kind of up or down to the relationship. It's pretty flat, and there's really no relationship. You've got people that didn't practice at all, scoring well, people that practice a bunch, scoring pretty well, people that didn't practice that were bad, people that did practice that were bad. So we're kind of all over the place. That's the idea behind what this is going to look like, okay? So if that's correlational research, when we do kind of a more what we would call a true experiment, where we're going to manipulate something, we also need to pay attention to several other things. One of those is, who are the people that we're testing? Where did they come from? How do we pick them? Okay. And there's a big question that we need to understand here, and it's about, are those people representative of the population of people we would like to generalize our study to? Okay, so if I have a question about if I exercise and I do resistance training in college-aged women, can I make their muscles bigger? I would want to recruit college-aged women, right? I probably also don't want to go to one of the gyms in town and recruit college-aged women from the gym, right? They may not be representative of all college-aged women. Conversely, I also don't want to go recruit 70-year-old women from a water aerobics class because they're not representative of the group of people to whom I would like my results to generalize, okay? So if you guys have seen some things potentially of late, we are not giving the vaccine to adolescents yet. I think maybe they've decided they've done studies in people that are like up to 13 or 14 or somewhere like that, but they've not done studies or they've not finished them where they're giving the vaccine to kids that are little. Okay, and so because they don't have that finished yet, you can't say that an adult or even a teenager is representative of an 8-year-old or a 6-year-old or a 5-year-old or a toddler or something like that. and we have to wait until we have data from a sample that is representative of the group we're trying to answer the question about. And so if we don't have this, that can introduce bias, then we're not going to be as confident in the results of that study being what we want. Additionally, we need to pay attention to something called selection and assignment. So let's say we did a nice job and we care about resistance training in college-aged women. I want to try to recruit people to do this, and I'm going to recruit college-aged women. I also need to pay particular attention to how do I pick the women? They're in the right age range, but how do I pick who I'm going to include? And then if I have a group that's going to train, and we're going to train, using free weights in one group, and we're going to train using machines in another group, and then we're going to have another group that's not going to train, and we're just going to see if there's any kind of time control groups with all of this. I also need to, have a systematic way of assigning people to each one of those groups. I can't, as a researcher, have people come in and look at it and then make some assumptions on, okay, I'm gonna pick all the people that look like they're really small and skinny and don't have a lot of muscle mass, and I'm gonna put them in my group that's gonna get the training. And I'm gonna pick all of my people that look like they already have done some resistance training or are a little bit more muscular, and I'm going to put all of them in the control group, right? I'm going to try to bias myself into picking people that I feel like might show the largest response in the group that's going to be doing the training, or the group that's going to get the drug or the supplement or whatever, because then I am biasing my results. And you guys would be surprised how often things like this can happen, okay? In an ideal world, we want something that we call random selection and random assignment, okay? Random selection would mean that of anybody that fits my criteria, any college-aged woman, that I'm going to randomly pick people from that large pool, okay, to be able to be in my experiment. In theory, every college-aged woman on OU's campus would have an equal opportunity of being in my study. This is ridiculously hard to do, right? The best way to do that is I'm going to get everybody's student ID numbers, and I'm going to go through and I'm just going to pick every third person from an ID number standpoint, or every ID number that ends in 7, and we're going to send them an email and ask them to be in our study. Okay, that's about as random as we can get with those things. In a very practical sense, this is not how research works because it's really, really cumbersome. Then once the people have been selected and they've agreed, then I'm going to put them all into a hat, and I'm going to draw names or numbers out. And then those people, okay, the first person I draw, you're in my heavy resistance training group. My second person, you're in my moderate intensity resistance training group. My third person, you're in the control group. And then I'm going to go back through again. And that way, in theory, then everybody has a relatively equal chance of getting assigned to each group. There is some systematic, relatively blinded way of doing it so that as a researcher, I'm not making that decision, okay? I'm not going to make that decision. And so this raises some problems and some issues. We would like for this to be what we call a randomized control trial when they do testing the vaccines and things. You show up, and they put your name into they give you a number, they put your number into a random number generator, and then you get picked on whatever it is that you're going to get based upon what that is. And the people that are analyzing your data don't see the people that are putting you into the groups, and they do a lot of things to have controls there, okay? Additionally, if possible, we always want to have a control group. We always want to have a control group, okay? And so the idea of a control group is a group that gets no treatment, a group that gets no exercise, a group that takes the same route to school as they always would. This is going to give us something about, if I don't do an intervention, you don't get any attention from the researcher, you don't get any excitement out of them taking a different route to school or something, then we don't want that to change. Ideally, in control groups, it tells us what sort of us not doing anything is going to look like. And then we're going to look then and see if we have a control group that gets no exercise training, your strength doesn't change over time. Or if it goes up a little bit, then that may tell us, okay, well, in a normal 20-year-old, your strength may go up a little bit over the course of 8 weeks or something. Okay. Ideally, in a control group, if you're getting diet or exercise or a drug or some kind of psychological treatment or something, we would like something called a placebo, if at all possible. And so a placebo is something that mimics the exercise treatment or mimics the drug, but it doesn't have the active ingredient. So like you're going to be in a placebo group for resistance training, which is kind of hard. You're going to come to the gym and you're just going to walk around, or you're going to come to the gym and you're just going to sit there, or you're going to come to the gym and we're going to make you watch a video of people working out or something like that. Okay. When it's a drug study, when you get a placebo, you get a capsule or a shot and it looks exactly like the drug, but it doesn't have the active ingredient of the drug. And that way we know that you're getting, it's not something about being in the experiment. There's not something about attention from the researchers. There's not some expectancy effect that we're getting from being in the study, then that can cause something, or we can at least try to experimentally control it and quantify it. Okay. Placebo effects are real. We will see that when we do our mental health stuff on Thursday. I can give you a pill and tell you it's a drug that lowers anxiety. And most of you that are anxious, that placebo pill will lower your anxiety for a little while. Eventually, at some point, that placebo effect wears off because there's no active ingredient. You may go back to your normal levels of things. But we use these to try to understand what is getting some attention or some kind of a treatment potentially going to look like, even if we don't have the active ingredient. So for drug studies and supplement studies and things, you must have a placebo group in order to do all of this. Okay. So I'm going to finish up today talking about something called Mills's canons, if only because this is one of the things that sits right with my liberal arts education that I got. And so it's from a guy named John Stuart Mill, who actually had to read when I was in college in one of our freshman classes on Western intellectual traditions, which I think is a lot like the class was basically whatever Emma's letters major is. That's what it was. But from him, there's a book that was published in 1843 called A System of Logic, Rationation, and Induction. And so what we have done with this, what you're seeing here, is something from a research methods book where we took these ideas that Mills called canons and they've put them in the context of using physical activity to treat health and make health better. Okay. But if we look at these things, for one thing to cause something else to happen, we need as many of Mills's canons to be met as possible. Okay. The first of those things is something called temporal sequence. Okay. In order for us to say that one thing caused another, that thing that you think is the cause must precede the other thing. Okay. So if I'm going to cause my can to be crushed, I have to apply pressure to the can and then it gets crushed. Okay. It's not that someone else crushed the cans. I was the cause. Does that make sense? You have to be exposed to COVID before you get sick, right? Before saying that the exposure to a person who is sick caused you to get sick, or I have to be in the presence of the virus first, then I get my symptoms. If you've not been in the presence of the virus, then your symptoms may be due to something that's not the virus. Does that make sense? So there's a temporal sequence, right? One, the causative agent must precede whatever the next thing is. Okay. We're going to skip number 2 for a moment. We're going to talk about consistency. Also, with consistency, when I am exposed, okay, or when I'm exposed or I have a risk factor, I'm always, or very, very often, I'm then going to have the health problem or I'm going to get sick. Okay. So one thing occurs before something else, therefore it may cause it. But every time that the original thing occurs, every time you're exposed to COVID, or very often when you're exposed to COVID, people are then consistently getting sick. It's not just, well, you were with this person and they have it, and then nobody, one person got it, but every other 10 people did. Or it only happens every now and again on all of that. The more consistent something is, okay, then the more likely we can say that one thing is causing another. All right. Also, ideally, there is what we would call a dose response, which we've talked about already in class. But a dose response is that I was exposed to a person who had COVID for 5 minutes. I have a little bit of a chance of getting it. I was exposed to a person that had COVID for 2 straight days. I have a much, much higher chance of getting it. So a little bit of exposure equals a little bit of risk. A lot of exposure equals a much higher risk. Or a little bit of a drug gets me a little bit of a decrease in my headache. A big dose of the drug and my headache goes away completely. That's the idea of dose response. Okay. So my causative thing occurs before the effective thing. When it occurs, I'm always very consistently seeing the reaction, and a little bit of exposure gets me a little bit of an effect, and a big exposure gets me something else. So dose response. The number 5 here, we're going to come back to strength of association, but number 5 is one that's kind of difficult for people. Okay. Number 5 is called biological plausibility. And this is one that people have a hard time kind of understanding, and it's oftentimes used at the start of an experiment. Biological plausibility means that within our current understanding of science and biology and how things work, we can come up with a reason or an explanation as to why one thing could plausibly result in something else. Okay. We can come up with this idea that whatever the flu does, when you get infected with the flu, it could plausibly lead to those symptoms that you're going to experience, right? You get virus, it affects cells in your lungs, right? When those cells get affected, then you end up with a cough. Or when those cells get infected, you may end up with pneumonia or something, right? So we have to have a biologically plausible reason a lot of times to really truly say that one thing should cause something else, okay? A side effect, let's just say as an example, a side effect of taking non-steroidal anti-inflammatory drugs like aspirin or ibuprofen or Aleve, okay, is stomach ulcers. So the question is it biologically plausible that taking an NSAID could cause a stomach ulcer? If you saw a bunch of people that had stomach ulcers and they'd all been taking Advil, is that biologically plausible? Well, NSAIDs work by inhibiting an enzyme called cyclooxygenase. You use the cyclooxygenase as part of inflammation. It makes products that make things hurt and bring in immune cells. Well, but in your stomach, cyclooxygenases lead to the production of mucus in your stomach that can help coat the stomach and prevent stomach acid from causing problems. So if we're inhibiting those cyclooxygenase enzymes by taking Advil or aspirin, then how long was I gone?
Not long, just it was like in and out for a minute or two.
It was like 2 seconds.
Like 2 seconds. Okay. All right. Wait, what happened? No. Wait. Let me go back. Share my screen. We did Mills's cannons. All right, so let's finish with this because the last couple of things are pretty self-explanatory. Let's finish with this. In your groups, guys, what did y'all come up with? Julia, what did you come up with for how many studies? What quality of study? Like what did how much research needs to be done for you to believe, right, that one thing is causing something else, or that something is safe and you're going to take it, or it's going to have some big effect? What'd you guys come up with? Like how much do we need?
Did you ask me? Because I wasn't sure because it froze. Okay, so we said that it's not really about the quantity, but it's about the quality of the research, that the researcher needs to have some sort of credibility in the area, and the research itself needs to be peer reviewed by people with good credibility in the topic as well.
Okay. That's very reasonable. All of those things are very reasonable. I can tell you sometimes that people that have good reputations can still do bad research. Maybe myself included. I don't know what my reputation is, but I know sometimes some of our studies are better than others in that way. Let me pick a different person. Ireland, are you there? What'd you guys come up with? Wait, nope, Ireland's not there. Sydney, are you there? All right, well, we're 0 for 2. John, I can see you. What did you come up with?
Dr. Black, your Wi-Fi is like cutting out
Okay,
pretty
badly.
terribly.
Okay, I don't know what's happening. All right, let's just call it a day. All right.